Oh, well, this is another series for in-depth presentations for Open Team, and we're going to hear from the OpenGeohub folks. They've had some initial conversations with Greg Ostick at RSI, and he recommended that Tom present to this group, and I'm excited to hear what he has to say. So with that, take it away.
Sure. Thank you for the invitation. Just to make sure that you can see my screen, if you can just confirm.
Yes.
Okay. So what I'm going to talk about is, I'll talk a bit about OpenGeohub, and then I will focus on soil mapping mainly, what's the progress of that, and then I will do a demo of the OpenLand map, which is our main global mapping system. So just to say about the OpenGeohub, so we co-found the OpenGeohub about 3 years ago, and the idea of the OpenGeohub is to promote open data and use of open source software, and also to promote practices for producing open data. We run summer schools. Summer schools we've been running for more than 10 years. And we also do help projects, international organizations to produce, especially global data sets. We also do regional data sets, for example, for Africa or for Europe. So that's kind of the main idea of the OpenGeohub. And then one of the main, flagship products of OpenGeohub, it's the system called OpenLand map. And as you can recognize, it's the name is inspired by the OpenStreetMap. The difference, of course, we're in no competition of OpenStreetMap. The difference is that we are focused basically. OpenStreetMap is about the, inside the cities and so like more like urban areas and just the topographic mapping. And we are interested in mapping environmental variables, soils and vegetation. So that's about the OpenLand map. I should also mention that it's something that we started about 1 year ago, and at the moment it's limited to a 250 meter resolution.
Hey Tom.
Yes.
Can you use like a headphone or something, or get closer to the mic, because it's a little hard to hear.
Okay, I can get the headphone just a second.
That would be great. Yeah, that'd be great.
What about now?
That sounds
much better.
Okay, great. So should I start from the beginning or just continue?
I think you're okay. You can keep rolling.
I just continue.
Yeah.
Okay, so so the OpenLand map we started about 1 year ago, and at the moment is limited to 250 meter spatial resolution, and also the we don't cover all the possible variables and layers. But we're making progress, and recently we got some funding, so we would like to slowly move to the 100 meter resolution. And also we would like to automate most of the processes. So maybe I should jump into the OpenLand map. So just to show you how it works and how can you use it for your own purpose. So I'm switching to this screen. Can you still follow my screen?
Yep.
Yep.
Okay. So as I said, openlandmap.org. When you land on the homepage, you can see also the things we do recently, and you can see that's the summer school I mentioned. And the first the basic layer you get, it's a land cover layer. So if I say, okay, I want to see where I'm now, you see I'm in the Netherlands in a little town of Wageningen. It's agriculture university town. We are somewhere in the center of the Netherlands. So if I zoom in further, So the first thing that people see, it's the land cover time series. So I can scroll and I can see how land cover changed in the last 30 years. This thing running in the background is a Geo server. We tweaked it a bit and we optimized it so it runs very fast. And so many people tell me, wow, this is so fast. And so I think we did everything properly. So people can have this impression like it's really the scrolling through the time, you know, and so you can see the changes. And I can also, it's a WebGIS, of course, I can go and look at, for example, transparency a bit and put the background imagery. So I can see that it's pixels of 250 meters, you know, there's limitations to that because of course, you cannot match it to the actual homes. But nevertheless, the accuracy is quite okay on the end when you look. So when you look at what is classified as urban area, which is the red thing here, you can see that it's quite okay. When you look in Europe or in US, when you look at the land cover map over the last 30 years, you know, you usually see like changes in urban areas. So obviously, Netherlands urban area has been growing over the last 30 years, as you can see. If I just zoom in very quickly. But the forested areas have also been growing. You know, in Netherlands they increase the forest area, forest cover every year. But when we go and look, for example, somewhere in Brazil, then we get a bit different picture. Then you will see that lots of land is actually converted. It's been converted from forest areas to some kind of cropland or some agricultural fields or pastures. And you can see then also, you can look at this area. So if I zoom in a bit more, I can see that again, it's a good match. And I can see that, so this, for example, this all used to be a forest here. These edges, this was a forest, and now it's been converted to cropland. So what we did, we mapped the soil carbon, and then we estimated what is the loss of soil carbon, just given the changes in land cover. So you can see here with the red color, it means there's a loss of soil carbon, and then the green color is actually a gain in soil organic carbon. And there are some areas, you see, there are areas that we estimated could be also gain in soil organic carbon. But most of area, unfortunately, you can see it's a large areas of red, and you can see that there's been a loss of soil organic carbon, especially like in wetland areas. So that's about the land cover changes. Maybe I show you also here. It's even a more distinct difference. In Indonesia, you see this area has been converted into a plantation. And you can see we calculate a huge, potentially huge loss in soil organic carbon. So all these areas you see are now plantations. And they used to be, if I scroll back through time, so we can see that this used to be covered in forest. I'm sorry, not this one, this one. So I can see this used to be, see this thing here, that was a forest, and it's been converted to plantations. And because of that, we estimate that probably there's a high soil organic carbon loss. This is like a peak area. So if I zoom in further, you see that it's been this is a plantation. So that's about the land cover. That, as I said, we have also climatic layers. So we have, of course, the temperatures for whole world. Let me zoom out a bit. So that's the whole world. Let's look at US. So here the temperatures. So what people can do, they can scroll through months. They can see how the temperature change. These are all known variables like temperature, right? This is all very known. But we also calculated standard deviation of monthly temperatures. So what you see here, it's how the temperatures vary in different months. And so the red color is a high varying, and blue color, it's stable. It's also very interesting to see how drastically things change. it also has to do then with vegetation and land use, etc. And so you can see this standard deviation of this thing. I'm not sure what is it related with. We're now just like looking at what could be, what is the exact relation between, different properties of land and land use and this variation in temperatures. And we also have a difference between daytime and nighttime temperature. This, again, red color is a high difference, blue color, small difference. So you can see the places where you have a desert land or this prairie, you have a high difference between daytime, nighttime temperature. And then in places like in Amazon, it's very stable. So the daytime and nighttime temperatures are kind of always the same. So that's also very interesting to see. We believe that these temperature signatures of terrain are very useful. So they tell you a lot about, for example, type of material you have. And also if we use that information to do soil mapping. And so if we know that, for example, there's a difference between daytime and nighttime temperature, we know that, for example, that could be a place where the clay content is higher because the clay content keeps the water. So it's the porosity of soil is much smaller. So it keeps the water, then it means it's cooler in the night. And then you have a high difference between the day and nighttime temperatures. So we use that to do soil mapping. And we did discover that it correlates with, for example, with soil textures. Speaking about soil textures, so here we have, for example, clay content. We mapped the clay content using ensemble machine learning and about 150,000 training points. So we spend a lot of time cleaning and integrating training points. And then, so you see this is, for example, training points of soil types. Then we try to find relations with the soil forming factors. We have now about 350 layers that we use for training. And we run an ensemble machine learning. Then we find fit model, for example, which are quite significant. Usually the R-square will be about 0.7, 0.8. And then we apply these models to make maps. And so I showed you here was a map of clay content. And it's a three-dimensional, you see, it's a three-dimensional map. I can move through depth and I can see how the clay content changes, going from surface to deeper soil. And then we also map the soil types. So here I show you somewhere in Ethiopia, I don't know. I can just zoom in to some soil type. And you see if I click on the point, it says it's a hub Plustalfs. And if I click on the prediction, it says hub Plustalfs. So you see the training points, they match the predictions behind. But some places we don't have so many training points. And so what happens is that we are lucky that we have the points, for example, from the United States or from some country, which has been mapped intensively. So there's lots of points. And then we build these global models. So we take all the points from the world, we build the global models, and then we apply them to fill in the gaps. And so people are surprised that we're able to map soils for the countries where we have no points. For example, like here, Kazakhstan, we have no points. And I think probably there's a good chance that we made probably the best soil map of Kazakhstan ever. So we have many of these countries that we have very little points, and we managed to fill in the gaps by using the power of using global models. So that's about the soil mapping. Then we also want to map the world without people. So that's a special section of Open Land Map is mapping a potential natural vegetation or potential land use systems. So what does this tell you? It's kind of, we take the training points from, for example, when it's about natural vegetation or native vegetation, we take the training points from protected planet area and from intact areas, and also from the studies of pollen analysis, so from like historic data. And then we build models, and then we apply them only using biophysical space. So we only use the biophysical parameters like the temperature, relief parameters, geology, everything which is just like, natural landscape. And then we get a map like this, and this one shows you the biomes of the world. So how the planet would look like if there was no people, basically. So it fills in all the cities and all the agriculture areas. And we're doing now together with GeoWiki, we are also producing a map of land cover classes, also potential land cover classes. So we want to make the same map as the European Space Agency recently made a map of the 100-meter resolution of land cover classes. So we want to also make a 100-meter resolution, but potential view, so people can compare, what is the full potential of the land and what is the actual. And we would like that this becomes like a reference for anyone to say, okay, if you, for example, want to discuss land degradation, you can then say, well, the potential of this pixel is much higher than the actual use, and then you can do that. You can kind of use it to quantify how much is land degraded and what is the gap between potential and actual. We also map the potential Fbar, so photosynthetically active part of radiation, which is kind of also used in estimating the biomass or net productivity of vegetation. So again, as I said, it's something that it's a planet without people, and you can see if I scroll through the months, for every month you will get a bit different pattern. Because the Fbar changes because of the seasons in Europe, at least, and in US, it changes, and so it can be relatively low in the winter times, and it can be very high in July, August, April. I don't know. So you can calculate also this potential Fbar. So taking out all the human influence, and then based on the if you take the actual, so this is the potential Fbar, but we have also the actual. So that's the actual Fbar, and you see that's also some missing months. And this Fbar is now controlled by land use, and like big cities like Paris, it will have a low Fbar, right? Because it's an urban area. But then if you look at the potential Fbar, it will be higher. It will be different. Because now we ignore that's a city. We just look at the biophysical properties, and then after we calculated the potential and actual, we can compute also the difference for the whole world, which is the you see here red means there's a gap, negative gap, so the potential is higher than the actual, and green means there's a positive gap. It means that the actual is even higher than the potential. So what's very interesting, I tell people in Netherlands, most of Netherlands is green. So the agriculture it's intensive agriculture. So the agriculture production makes the country greener than it will be assuming just natural conditions. And also, if you look at the delta, it's very green. So delta, because of this, is all irrigation system. So this would have been kind of semi-desert, but now it's all irrigated. And that makes it much greener than if you would have without these irrigation systems. But then you have many areas where you have, for example, here it's all red. So I'm not sure actually why. I mean, I didn't have time to really zoom in all these differences. So we just computed this and we said, okay, this method is correct. We published a paper, but I'm not sure many areas they are redder, and I'm not sure whether it's because of the land degradation or it's because of because this data for the with the actual Fbar, they're based on 3 years. So it's a 3-4 year data. So it could be there's a year with the Fbar was a bit lower because of it was a dry period or a couple of years with drought. So they are quite different. Of course, you immediately see that most of the planet it's red, and especially if you look at the tropical areas, you can see that all these areas in Africa, they've been cut down and converted to agricultural areas. They have now much lower Fbar from the potential, and it's the same thing for the Brazil. You can see it's a much lower Fbar. If you're interested in looking at this, methodology behind this, what you can do is you can access this description, and then you see there's a paper that explains how it's been calculated. And so that, as I said, we calculated the potential biomes, and we calculate potential Fbar, and you can see you can follow that. So you see the data set is fully documented. You can also download the data. So we put all our data, we put it either on Harvard Dataverse, or we put it on Zenodo. So you can see the data is also accessible, and you can download it. You can load it to your own GIS. You can also play with our GeoNode. So we made a GeoNode which serves the WMS, and you can see you can make your own visualization, and you can embed this visualization into your websites, or you can embed them into your WebGIS. And you can also customize the visualization, so you can make your own legends and things. You can also, everywhere you click, you will get the value. And this is served through an API. We call it a LandGIS API. And this API can be embedded again in if you're a developer, you can embed it into your applications. You can query you can do many hits on this. So we do have lots of people accessing and using. I can actually look here. Here's the map of the users in the last 1 year. So we are somewhere now, I think something like 15,000 people accessing. And so you can use it to query lots of things, and you can also program and automate it. And as I said, you can also embed, if you want to embed it into a page, then you will just put this thing. You see, we have a relatively simple bookmarking system where you can pick up the layer name, and you can set opacity and zoom level, and then you pick up the center and the background map. And that allows you to, if I open this URL in another tab, I get exactly the same view. So there's no difference. So basically, it allows people to communicate about so land cover changes, land potential, vegetation, climate. So people can communicate without really understanding GIS or cartography and anything. So we try to get these topics closer to people. What else I want to tell you? Yes, we also develop everything on GitHub. So you can see that people ask questions, and all the code is exposed. And so if you want to see how the soil maps are made, you just go to, for example, soil, and there's a code that explains how the predictions are made. This is our code. I mean, I'm not going to go through that, but just to give you an idea, we would like to reach a level of full reproducibility, actually. So we allow people to, if somebody says, oh, how did you get this pattern? I don't understand. We say, well, take a look. This is the model tuning, model fitting, predictions. These are the parameters we get. This is how we do predictions. So it's all exposed, and people who have a significant infrastructure who understand spatial analysis and machine learning, they should be able to go and reproduce our results. This is about the GitHub. The last thing I want to say is about the community. So we have also people now submitting data. So we had a couple of people contacted us, and they said, well, we made these layers. Can we host it on your website? Then we have a system where we have some minimum requirements. It has to be open data, and it has to be documented, and it's ideally should come with a description, etc. And people have to maintain it. And then we give this also we publish third-party layers, so we do basically hosting. If the data is 250 meters, then it's not so complicated for us because we have still quite some space on this server. If the data becomes a bit more tricky, or if the colleagues, they want some special visualization, then we have to spend some time. So this was a request by the spatial ecology. They wanted to have map the stream flow of water. This is a data set, I think 50 years. And so you can see how sorry, I have to turn this on. This one, sorry. So this is the water discharge for last 50 years. As you can see, some areas they changed a bit, some changed more. And if I click somewhere, what happened, I will fetch all these 50 years. And I can also then plot that, and so we can see how things changed, and which year was the peak. So you can trace back. I mean, I don't know if there was some excessive rains or floods, so I don't know. But you can trace back and you can look for every pixel, the history, basically hydrological history of that. So that was, again, as I said, that the data and the visualization was prepared by spatialecology.net by Giuseppe Amatulli and his colleagues. So that's example of contributor data. As I said, we would like to now move and start mapping the potential natural vegetation and soils and land degradation. We would like to start mapping at 100-meter resolution. I think that's the next level. We have all the spices. We have basically, we have enough skill and we have enough remote sensing data to do that. The problem is just the data volume increases about 5-6 times than what we have now. And also the computing time goes also about 5-6 times up. And so it means that we have a much higher cost. And when you think about it, if you say, well, it's, you know, going from 250 to 100 meters, it's only 2.5 times, but it's about 5 times higher volume and higher cost. So if you had a project, I don't know, $100,000, then we have to move to the $500,000. Of course, it's not exactly $500,000, but you know, it's definitely like at least, you know, 2-3 times higher. So that's the problem we are facing now. But we would like to scale up and we would like to further optimize a prediction. So at the moment, some of the predictions they can take 1 week of computing, but we would like to bring it to a 24-hour or even like overnight. So when you do the predictions next day, you have the new maps. But so that also again takes a different infrastructure, and we have to prepare data for that. So that was about OpenLandMap. I think that's the thing that's most interesting to you. And you know, I don't know how much time I have, but I think it's good that maybe I stop now, and that you maybe ask me questions, and then we can go and zoom in on different things, something that's like really interesting to you. Is that a good suggestion?
I think that sounds great, Tom. That was really fantastic. Thank you so much for sharing. I'm sure there are going to be a lot of questions, so I will hold mine, of which I have many, until and give open the floor to the group. And we have until the full hour, so that's 1 o'clock East Coast time. So we have another 25 minutes here for questions. So feel free to unmute yourself and dive in, folks. And we've got Will Gardner. Perhaps you had texted or chatted a couple questions, and we've got one from Craig, and I think there's Daniela had another question. So, Will,
okay.
Yeah,
please sort them and shoot them.
Hi, this is Will. I was curious about whether you're able to pull like data for regions, so like query via bounding box instead of a point. Do you support that?
Yeah, we have the web coverage service. So maybe I'll show you that. So let's say this is Netherlands and looking just in land cover. So there's the web coverage service, and this one allows people to pick up a bounding box. So you will pick up a bounding box, and that will download you only that bounding box. So you get let's see, I will now save it somewhere in downloads. And this bounding box, if I throw it here on the map, you will see it's just I locally downloaded some block. It was in Latlan, so I have to switch here to Latlan. And so you see that's this block. So you can do with the web coverage service. It's quite powerful. I mean, you can do lots of subsetting, but not for polygons. So for polygons, you will have to then download the block and then crop to polygon. But it is possible. You don't have to download the whole thing.
Okay, great. And that was in which section of the GitHub?
So there's the section on web coverage service.
Okay.
This is called this functionality where you take a layer and you say, I want to just fetch a block. It's called web coverage service.
Okay, and I saw too on the map when I was looking at the network requests and you load in stuff from, it's the WMS server.
Yes.
Can you use that for similar functionality?
The web mapping service is just PNGs, right? People don't, they miss that, but the web mapping service is just the view, just the PNGs. So it's not actual data. So
okay.
you can get also from WMS, you can get the PNGs, you can download them. But it's just the colors. This thing, when you do web coverage service, you get actual, like the raw data, the thing I showed you here. This is the actual GeoTIFF, a part of the GeoTIFF. So that's the actual data service. And it's very fast. As you see, it works very fast. If you do little chunks, but as soon as you move to above gigabyte, it will stop because we have to limit it. Because if we have people like requesting, gigabytes, they crash the server very quickly. So we limit to about 1 gigabyte.
Wonderful. That's very helpful. Thank you.
Sure. And the web coverage service you can open also, you can open it in, for example, QGIS. So it looks like this. You specify the web coverage service or WMS. And then you open this map into QGIS, and then you can do computing, you can do cropping. So it's not like this one example I showed you with the URL, but you can also just open in QGIS, and then you say this is the URL, right, to open, and then it will show the layer you want. And then you can do cropping and things.
Okay, got it. Thanks.
Great. We had a question from Craig, which I think was along the similar lines.
Yeah, it's really retrieving data from multiple layers from a point source. So I can see how you can do the JSON calls on individual layers, and it's really neat. It's really great work. So, but can you just provide long data and for a single point and pull back data from across layers?
Yes. So yes, that's also explained here. Let me see. Oh, we have also copy now, by the way, of all the data. We just put it on Google Earth Engine, so you can also access everything. If you're better in Python, you can access through the Google API. But we have a functionality to do, for example, using the JSON files. So you can prepare like 50 files.
A script, yeah.
Let me see, where is that example? Yeah, this one. So you prepare a GeoJSON, and then you can loop. You can say, I want to download these 20 layers. We have about, I think, 400 layers. So you can say, I want to download these layers, and then you can do up to 50 points. We also had to limit, because it's computational. I would like to increase it to like 1,000 points, right? So then you say, these are my 1,000 points, and these are the layers I want. And then you would just do curl, and then it will return the results as a JSON.
Yeah, it's very neat. Thank you very much.
Yes, and that for now it works 50 points. It's very fast. It's you can get many layers. You have to loop it a bit, but if you, I hope that we will increase the infrastructure, so we can allow people up to 1,000 points. But I cannot promise you now.
Perhaps, Mark, do you want to jump in here? You had a question about the soil organic model.
Sure. Yeah. Hey, thanks, Doran. And hey, really nice presentation. And this is really impressive. I've been hearing about this for a while, and it's great to see your demo here. I was curious if you could describe the model that you use for predicting soil carbon, and I was just curious if it differentiates between organic carbon and inorganic carbon.
So if the carbon map is here, let me open it. So these are the global predictions of carbon. The dark red means higher carbon, obviously. So I don't know, we can look somewhere in US. This is, by the way, all organic carbon. We don't map the total carbon. So I don't know if you know, the organic carbon is the organic matter, and total carbon includes also if you have a limestone or rocks, or you have the concentration of carbon, which is inorganic in the soil. So we only map the organic carbon. We map it with the ensemble machine learning also. It's also 3D model, but it's a bit more tricky, soil organic carbon. And I'm still getting problems. We have to do another run, I think. I just spoke with some people. So like for Brazil, you see, we get the carbon increases with the depth. And I have no idea why this happened. I double checked the point data from Brazil, and I have a contact, a colleague. You know, we work together in Wageningen, and so he's responsible for the point data for Brazil. And he told me, no, the point data is fine. I said, yeah, when I use your point data, I get this carbon with the depth. It's as you go deeper for the Amazon basin. He says, I checked the points; they're all fine. So I have to like rerun everything and zoom in. So carbon is like very tricky because it's like patchy. The distribution is very patchy, and also it's a very skewed distribution. So it's a very highly like non-linear, non-normal variable. But we do get, you know, we mapped lots of carbon pools, for example, in Africa, where we have no points. You know, we kind of extrapolated the global models, and we find all these pools, and especially in Indonesia, we find a lot of carbon still in the soil. Potentially. So that's the carbon mapping. So my answer to you is no, we just do organic carbon, and we have a single model for whole world. So places with what I call organic soils. Organic soil, usually it's like organic carbon content for the thickness of more than 30 centimeters above 12%. So that's a classified as organic soils or histosoils. And we map both organic soils and mineral soils. We map them together, so it's a single model. All the models we use are tree-based models, so stratification is not needed. Stratification is built in the model. So if you have like a jump, you know, if you go to some area, I mean, if I look here, you know, you have a jump in values because potentially there's some polygons or some units which have a higher carbon, and then they're just mapped by the model. So these are all tree-based models like random forest, neural nets, gradient boosting, support vector machines. Support vector machines, though, it's not completely tree-based, but like random forest and you know, all the decision tree systems or neural nets, they're all tree-based. So you can incorporate jumps.
Could I ask a follow-up question?
Sure.
Yeah, that was really helpful. Thank you. I'm just curious if you could describe what the inputs are, what the remotely sensed data are that are being used to drive the model, because this is super interesting, especially since that you're using neural networks and machine-based learning. Just curious what the inputs are that are driving it.
Yeah, so we do different covariates for the bit different for vegetation mapping and for soil mapping. For soil mapping, the key is to get very good landform derivatives. So landform parameters like the hydrological properties of terrain, potential hydrology of terrain. We also have these MODIS land products. They are now 20 years or something. So they are quite complete, and we calculate long-term monthly averages. So if you look at the vegetation index or temperatures, you know, the maps I was showing you, we calculate the standard deviations and long-term averages, and also differences between daytime, nighttime. Then we also have, we use geology map that we have. It's not the best, it's one of the poorest layers, but at least we have geology incorporated. And we also use different maps produced by groups, which, for example, for example, map of wetlands of the world, and then also there's a map of so groundwater depth. So there are different layers produced by groups, and we clean them up, and then we prepare them, downscale them if needed, and we prepare them for soil mapping. So now at the moment we have about 350 layers for soil mapping. Let me just see if I remember if we have put all the layers. I think they should be somewhere here in the tables. So here you can see, well, actually maybe this is not so the best to read. Yeah, but there's a list of all these layers, and so it's not the best thing to read. But there's about 300 layers, and as I said, they usually represent the climate, the landform, geology, hydrology of terrain, so all the soil forming factors. So there's this CLORP concept of soil formation, climate, relief, organism, barren material, time, blah blah. So we try to represent that with the data, and then we come up to about 350 layers in the back. But for every variable that we map, it can be different. Layers can be more significant. Sometimes we get that the relief is most important. So like I have here a mapping of soil hydrological properties. And so if you look at somewhere in US, you can see that these valleys, you see the valleys are quite visible. So it looks like the relief is most important for mapping. So this is the field capacity water, so the soil water at retention curve. And you can see that its relief is pops up as something very important. So you have places where you have valleys and river valleys. You have usually more clay soil, and this clay soil keeps the water. And so you can see this comes up. So every property can be different, and also these tree-based models, I mean, because we have so many covariates, they can show one type of relationship in one continent, and the other continent they show a different type of relationship. So they're not like in regression that you have a single coefficient. I mean, this is a hyperparametric model. So if you have enough data, it will locally adjust. That's what I really like about like tree-based machine learning, that you can spatially adjust. If you have point data, and in one part of the hill you have this type of relationship, and on another side of the hill it's a different relationship, it can be incorporated. So it's a hyperparametric model that incorporates all the nonlinear splits, and that's what I really like about machine learning. That's why actually I pushed myself to start using machine learning for spatial data about 5-6 years ago. And since then, I realized, okay, I made some mistakes and I overfit the data and I ignored some properties. But it's getting better and better. I have to say, we do cross-validation, we do down spatial cross-validation. We try to incorporate as much as possible the sampling locations. We also try to incorporate geographical distances between points and things like that. So we're doing a better and better spatial machine learning.
Awesome. Thank you very much.
I have a question. If we don't have somebody else to jump right in, I was wondering if you might speak, and I'll invite Greg or Jeff Herrick to jump in here too, on the process for accepting the training points a little bit more. We have, within the community, we have field data tools for in-field data collection. So I thought maybe you might spend a little bit more time on the process for that, and I'll also just see if Greg wants to jump in a little bit for a follow-up.
Yeah, I would add one more thing there. I think some of the data that people are collecting isn't kind of international in scope. So, how can you accept, and how can you manage and display data that might be like may have only been collected on one person's farm, for example, or within one county, that you can't make sort of international in scope. Is it relevant? Is that something that you would consider, or yeah, how would you handle that?
Yes, it's the data can be. I don't know if you can still see my screen, right?
Yep.
This is still unpublished. This is land cover, potential land cover map of the world. So we're doing in parallel to the actual land cover map. We do a potential, and you can see. So in the back you can see the actual land cover, and this is the potential. So we have the points. I mean, they can come from local. They can be from a country or from individual people. They can be regional, like a continent, and they can be global. And it's not a problem. I think this, like if you have many local, like if you take many local data sets and you combine them, and you can get a nice coverage. But the problem is if you have different methods, and if everybody invents some different way, they collect data, then you have a problem. Then it's not only that you then have gaps, but you have to harmonize and standardize the data. It sucks up so much energy. And I feel that for these projects that we've been doing on Open Land Map, something that really slows us down a lot was the harmonization, standardization of data. And so that's my answer to you. Is not a problem if the data is local or if it's just a single person, but the problem if everybody uses a different, measurement stick and different methodology.
Great, thanks.
I think you're making the argument for some of the tools that that this group is working on developing for creating
yes.
tools to standardize methodologies in the field.
Yes, absolutely. If you can help there, if you can, like for example, soil classification. I did a master degree in soil mapping and in geostatistics and pedometrics. And I remember the soil mapping, I was like started looking at different systems. Every country invented their own soil mapping system. You don't have it like in biology. It's like biology now converged into a single, in GB, if you have a single taxonomic system, you can call them in a local language however you want, but the translation is seamless, it's all solved. With the soil classification, you have every country they were created, they made their own classification, and then you go like, okay, let's map the classes of the world. And then so what does this international, there's that one. Eventually we went for the USDA system. And I think it's on the end of the day, it's the best described system, and it's been an enormous resource invested into that. And it kind of covers all the climatic zones, and so we can use it. So we went using the USDA system. But then every time I go and speak with people, they say, oh, why do you use USD? Why don't you use FAO? Why don't you use this? And I have to say, I feel like it just slows me down. Because on the end of the day, we're not interested in politics, right? We're interested in understanding the soil, climate, vegetation, natural cycles and things like that. And we are interested in getting the best accuracy, providing people with the best information so they can make decisions. And I hope you agree with me on this. It's not about politics, but we finish often talking about the politics of data. Yes, I call it the politics of data.
Yeah, absolutely. We're getting close to the end here, but if you could just quickly, I'm also interested in the sort of the inverse of being able to pull down essentially and locally host a small subset in offline for offline data exploring. We have a lot of folks who are creating data visualizations at a regional or even farm level. And wondered just a quick comment in terms of your platform's adaptability for that sort of use case.
Yeah, if you want to have just for a local region, let's say, a state in US, you want to get open land map data, I would advise using web coverage service. You have to make some code, and then you clip, only the data that you're interested in, and you have it locally, so you don't need to be online. And you can also, as I said, the Open Land Map is now completely on Google Earth Engine. So if you're good in Google Earth Engine, you can also clip. Look, our idea is to make open data to enable people. There shouldn't be any obstacle for you to grab this data and use it. So there's no hidden agenda here, right? It's really, we are a foundation, we are not for profit, and we really want to make an OpenStreetMap type of system where people feel ownership and people exchange data and they access it without a problem. And if you know OpenStreetMap, you know you can access data. And so one way you can increase the usability of data is to increase the accessibility. And accessibility means often, for example, you have to have a diversified access. So you have to have access to people that use GIS, that use WebGIS, they are developers, they have mobile phones, whatever. You have to diversify the access. And so we try to do that by putting a copy of data, for example, on Google Earth Engine. Then we have also a copy of data on Zenodo. And some people do want the whole world, and they do want to download 20 gigabytes. So you can do that. You can just go to Zenodo and download the layers that you want for the whole world. So we diversify the access to data, multiple copies often, and also we have multiple standards. We have web coverage service, we have the REST API, etc. So you have to diversify the access. And if you do everything properly, then nobody complains. And we don't get many complaints now to the data access. We get now mainly complaints. People say, well, I have some artifacts, or they say, well, how do I use this data? What does it mean? What is this layer? And so that's where we get a bit of complaints. And but otherwise, access-wise, I think we're doing very well. Very little complaints there. And I can see the web traffic. I can see the people are downloading and using data.
Quick question. When do you think you'll get to 100-meter resolution, and what do you need to get there?
Well, as I said, I would like to get really quickly into it, and I know we have to scale up our infrastructure, but I started working on that, and of course we're going to go step by step. So we will first make a couple of layers in 100-meter, and then we see how nasty does it get, with the data sizes and things. And then we're slowly going to convert everything, but it might take like over 1 year. Now we want to do the potential natural vegetation 100-meter, and then also remap all the most important soil variables in 100-meter. 100-meter is really almost field scale. That's something where the farmers will say, okay, this is my piece of land, and the 250-meter, it's not, you cannot make field scale decisions. With 100-meter, you're getting close to that. Yes.
Yep.
My dream is to do like 30-meter whole world. That's
that'd be amazing.
We have the point data. We have the knowledge. We develop code. I mean, I made like 10,000 lines of code in the last 5 years, and so there's a lot of experience. And for me, this it's not a question now anymore of how methodologically, and but the issue is the infrastructure. So I cannot now promise you're going to do that because we don't have the infrastructure.
Well, thank you so much. This has been hugely helpful and inspirational to this group. I hope you'll all join me in thanking Tom here at the top of the hour. And we're really looking forward to following up with you as we proceed with OpenTeam and our next steps.
Sure. And did you mention Jeff Herrick maybe?
Yes.
So he's connected now. He's watching.
Yes.
I just want to send him my best regards. He's been very kind to us, and he connected us. Even here in Europe, he came from US to connect us, and he was a really binding element for the lots of this global land information. And so I got lots of also ideas when I was visiting Boulder and New Mexico. So I just want to send him my best regards and thank you for this.
He had to drop off 2 minutes ago, so he missed your thing.
Okay, no problem. Then it's even more genuine than that I mentioned this to you. Maybe it's more important that you know that.
Great.
Okay.
That's terrific.
Guys, good luck with your work and congratulations on winning that funding. I've been reading a bit about it, and I'm looking forward to meeting you also in real person.
Likewise. Thank you all, and we'll see you at the next in-depth session. All the best.
Okay. Bye-bye. All the best. Bye-bye.
Thanks.
Bye-bye.
Bye.
Thanks. Bye.
Thanks. Bye.
Bye.